This is Module 5A, one of three submodules, 5A, B, and C, for open systems. We're going to look at open system energy balances. And as a first example of open systems, we're going to look at heat exchangers, which take heat from one fluid and put it into another fluid. Open systems energy balance are in equals out plus accumulated, familiar balance equation. And we'll first look at what's called a differential balance, or an energy per time balance. Then we'll look at an integral balance, which is a total from one time to another, how much energy went in or out of the system and how much was accumulated or stored in the system over that time interval. Differential balance, the most common, and I like these. We have, first of all, the mass flow times the energy per mass coming into the system plus any heat that may come in equals mass flow times the energy per mass out plus the work out per time plus the change with time of the energy of the system, ddt of E of the system. Now these little dots here mean per time. So that's a flow, a mass flow, a heat flow, a work flow, and all that will have the same units, energy per time, as the storage, ddt of the energy of the system. Now we're going to define this energy per mass. This theta term for the energy per mass is the internal specific energy plus P times V. These two together make up what we call the enthalpy. And so you have the flow work plus the internal energy, plus the kinetic energy per mass, which is 1/2 V squared, plus the potential energy per mass, which is just G times H. The energy, the total energy of the system, would be its internal energy. No flow work because this system is the mass that we're doing the balance on, and it's already there. The kinetic energy, now I've written this in capital letters because that'd be the mass of the system times V squared of the system. And PE, capital PE, would be the mass of the system times G times the height of the system. Now we'll look at the change in energy of the system. That's a change in, it can be due to a change in phase, a change in temperature, a change in height, a change in velocity. All those things contribute to the change of the system itself, a delta U, delta PE, or delta KE. Or you could have no change. If there's no change in the system itself is not changing with time, and we have many systems that this happens with, then we say the partial of any property of the system with respect to time at a fixed position is equal to 0. That's the definition of steady state, where the change of properties with respect to time is 0. Now suppose we have a system as our radiator in our car. Here we're putting water in, hot water in, taking cold water out, and meanwhile air is blowing across the radiator in such a way to cool the water from your engine. If we look at the temperature when we start the car, first thing you start the car, over time that radiator is going to heat up and all the liquid in it is going to heat up, and that'll increase with time until finally the radiator will be warmed up, the car will be warmed up, and you won't see the temperature changing anymore. You'll have a constant temperature there. Once it reaches that constant temperature, we have what we call steady state. With an integral balance, we'd look at the integral, or the total of the mass in times its energy. It's basically the integral of a differential balance. So we integrate all those flows, which would be the integral of the mass times the energy in. That would be the sum of all the energy coming in, plus the sum of all heat in, minus the sum of all heat out, minus all work out, is equal to the change, and this is important when we get to charging problems, mass final times the energy final of the system, minus mass initial times the energy initial of the system. Again, that's important for charging and discharging processes. We won't get to that until Module C, 5C, but it's important nonetheless. Now, equipment frequently operated at steady state, and I want you to master these types of equipment. Heat exchangers, turbines, compressors, and pumps. We'll get those things running at steady state, and we try to keep them running that way. Valves, nozzles, and diffusers. Lots of steady state equipment that we'll be looking at where the input and the output are balanced. If it's at steady state, then what goes in equals what goes out. The change with time of the system itself is zero. So we would say in equals out, accumulated is zero. Oh, here's another one, mixing chambers. If I'm mixing two fluids together and the third one comes out. Another example of an open system and that we try to operate at steady state. Let's look at heat exchangers. So I'm going to spend a little bit of time on heat exchangers. And there are several types. There's one where no phase changes, and that's, I think your radiator is a good example of that. The air comes in from outside and the air is heated up as it goes past the radiator. So it doesn't change phase. And then you have inside the radiator the water coming in hot and leaving cooler. So it's not changing phase, it's just changing its temperature. I just call those exchangers. Boilers and evaporators, you do have phase change, so at least one of the fluids is changing from a liquid to a vapor. Another fluid may just be changing temperature, but at least one of the fluids is boiling or evaporating. Condenser is the opposite of boiling and evaporating. In a boiler, you put heat into the fluid that's boiling. In a condenser, you take heat out and it goes from vapor to liquid. Here's a kind of a schematic of a heat exchanger, and this would be like your radiator. You have air coming in and air going out. You have water coming in and water going out. So the water comes in, like this is a car radiator. The water comes in hot, and I should have that changing, to blue or something. It's cooling down as it goes through the radiator, and the air picks up that heat, and you have cooler water coming out. Here's another view of it. The air comes in across the radiator. It's usually a cross-flow type system for the air. And the water comes in hot and comes out cooler. The air itself comes in cool and comes out hotter. So you're exchanging the heat from one to the other. So here I'll draw it this way. The water is the red, hot. The air is the blue, cool. And the heat goes from the water into the air. If we say it's a steady state, then what goes in equals what goes out, or in equals out plus accumulated. Whenever you have a steady state system, the accumulated term is zero. In other words, it's not changing with time. So the energy balance becomes, if I neglect the velocity of the water and the air, the changes in velocity of the water and the air, and they're fairly small, then the energy per mass of air is the enthalpy. So the mass of the air times the enthalpy of the air in plus the mass of the water times the enthalpy of the water in is balanced by the same going out. So it's fairly simple energy balance. If there's no phase change, then we can say for an ideal gas or for a liquid that doesn't change phase, delta H is approximately equal to Cp delta T. So I can rewrite this equation and rearrange it a little bit. All I've done is a little bit of algebra on this. And we have the mass flow of the air times its Cp times its temperature out minus temperature in. That's the change in temperature of the air. It raised its temperature, so out minus in is positive, is balanced by the mass of the water times its Cp times its temperature in minus its temperature out, because the water is dropping in temperature, losing heat. That amount of heat transferred is the total enthalpy gained by the air equals the total enthalpy lost by the water. Complete exchange of heat between the two fluids is equal to Q dot. So the heat transferred internally in that exchanger is Q dot, we'll call it. Now, I like to draw a diagram to show, I like to picture what's happening to the temperatures if I sketch this out according to the water going across the exchanger. As you can see, I've drawn it going from hot to cold. It drops in temperature, whereas the air came from cold to hot. Now, all along this heat exchanger, physically, in any point in this heat exchanger, the hot has to be hotter than the cold, and this temperature difference we call the driving force for heat transfer. The greater the temperature difference between the air and the water, or the water and the air, the faster the heat will transfer, and the smaller your heat exchanger will need to be. And that's important in design for later on. Let's take an example. Air enters the heat exchanger at 25 degrees C and exits at 15 degrees. Chilled water enters at 5 degrees and exits at 18 degrees. Now, interesting, you have the water actually leaving hotter than the air is leaving. The only way to do this is have some sort of countercurrent situation, and I'll diagram that for you. For a cooling load of 5 kilowatts, determine the required air and water flow rates. So these are the sorts of problems I'd like you to be able to do. You set up your energy balance, and you calculate the mass of the air times its Cp, T out minus Tn, just the energy balance we just had. Then you plug in the numbers, is equal to Q. And remember, Q, we said, was 5 kilowatts, the amount exchanged between those. So since I know Q, it's equal to the Q lost by the, gained by the air, or lost by the water, and we can solve that for the mass flows we need. Mass flow of the air would be 0.498, and mass flow of the water would be 0.092. Now let's look at a boiler. Suppose we want to make steam. The way we might do that is take a hot gas, hotter than steam, and run it through the steam, and as the gas cools, it'll exchange its heat into the water, and the water will start to boil. So in a boiler, we have a phase change. Now, what could be happening to the temperature of the water? I could be putting this water in at 212 and taking it out at 212. And a lot of students think, gosh, it's not getting hot. But it is. It's not getting hotter in terms of temperature. But its energy is definitely going up because it goes from a liquid to a vapor. The gas is cooling, going to a lower temperature, and that's a sensible energy change. But the steam, creating steam, is a phase change, and there's a lot of energy involved in doing that. So we'll do the energy diagram on a boiler. And here we have the hot gas, drawn that in black, and the water coming in red. So maybe we bring the water in a little below the boiling point, and then we get up to temperature of boiling, and then it'll boil at a constant temperature. Now, I've assumed that there's very little pressure drop across this heat exchanger. And in truth, there is a little bit of pressure drop across the heat exchanger. But for the time being, we're going to neglect that. We're going to assume for heat exchangers, delta P is approximately 0. And so the delta P is very small for heat exchanger. And so if the pressure doesn't change, then as the water boils, its temperature won't change either. So remember that from saturation. Once the pressure is fixed and it's saturated, the temperature is also fixed. If we do our energy balance, then we have the heat loss of the gas is simply mCp times T out minus Tn. The heat gained by the water is mCp times T boiling, that's the temperature it's going to boil at, minus Tn. So that's the little bit of increase in enthalpy as it gets to the boiling point. But most of your energy comes from this HFG. And remember, HFG is the enthalpy of the vapor minus the enthalpy of the liquid. So that's your phase change energy there. We look at a condenser. It's basically the opposite of a boiler. We'll take a hot vapor and cool it down and turn it into liquid. And we'll do that by we'll exchange that heat, the heat that's lost as it goes from vapor to liquid, that heat will go into the cool fluid that you're using to condense with. So that's basically the opposite. And it would look something like this. We'd come in with a hot vapor, cool it down to its, well, boiling point, but really at this point we'll call it its condensing point, same temperature at a given pressure. It condenses at constant temperature, assuming pressure is the same. And then once you get all the way condensed, you can subcool it a little bit and come out with your product. Meanwhile, the fluid that's accepting that heat, again, heat always goes from hot to cold, so the heat's going this way into this cold fluid, and this cold fluid is heating up as it goes. We can have a condenser and a boiler together, and as you see, neither of the fluids is changing temperature. This could happen as long as the hot fluid is hotter than the cold fluid. I've got these reversed. Well, that's okay. This is black being the hot, the red being the cold. As long as the hot is hotter than the cold, if it's changing phase, it can still be losing energy. The condensing fluid can be losing energy as it goes to liquid, and the boiling fluid can be gaining energy as it boils. So the temperature doesn't have to change. Boiling and condensing are great ways to move energy around because the heat of vaporization, and particularly for water, water is an excellent working fluid because it has such high heat of vaporization, 2,258, depending on the pressure or temperature, 2,000 in this case, 258 kilojoules per kilogram at 1 bar. Whereas to get that much change in energy from a vapor, gosh, you'd have to change it 1,000 degrees here. Cp of the vapor being steam being 2, and Cp of the liquid being 4.2, so you'd have to change the liquid about 500 degrees. The vapor you'd have to change 1,000 degrees to get that same energy change. So you can really move a lot of energy just by condensing or boiling 1 pound or 1 kilogram of steam. All right, common assumptions for heat exchangers. No heat loss. We're assuming that all the heat that goes from the hot fluid goes into the cold fluid. That's not always true. You have to be careful. In the real world, you may find a heat exchanger that loses heat to the surroundings as well as to the other fluid, or to the cooler fluid. And we're also assuming, as I alluded to earlier, that there's a low delta P. We're going to neglect it. Assume it's approximately 0 for each fluid unless you have other information. Also, we're assuming that there's a low change in kinetic energy and a low change in potential energy, so that the energy per mass is just the internal energy plus the PV term, or enthalpy. So we've looked at open systems, and we've indicated that mass enters with U, PV, kinetic energy, and potential energy, and we'll address these kinetic energy and potential energy with different sorts of systems. We looked at heat exchangers. And now onto your homework. You need to read Chapter 5. You're going to get a lot more than heat exchangers, but this is all coming fairly quickly, so read through the whole thing and start working those problems with heat exchangers. Work them right away. And then take a look at this problem. This is a little heat exchanger that you have, probably have one around your house somewhere. A blow dryer rated for 1250 watts. Well, actually, it's not quite a heat exchanger. Really, you've got electric energy coming into your blow dryer. And let's just assume that 1250 watts goes all into the airflow. Let's take a look at this problem, write down all these specifics about it, and then calculate what the airflow would be to accomplish these following changes in temperature. I measured this with our blow dryer, and I'd like you to just see what kind of airflow you have to accomplish those sorts of temperature rises. So very good. That's the Module 5A.